So when I worked in the industrial laundry, we would wash 36,000 pounds of laundry per day. 36,000 pounds. Primarily, this was things like table linen for restaurants, bed sheets for hotels, things like that. Things that people would be using and coming in contact with on a regular basis in a commercial setting. And so it was really important that as we're washing these sheets that one, we had to use more raw chemicals. We can't just buy you know, 17 crates of Dawn detergent. We actually have to get the raw chemicals that Dawn would use to make their soap and pump those into our system. Well, the problem with that is it's a little more of a refined chemistry. We had to do the chemistry in-house. And one of the things that could come out is the pH. So if I've got a bed sheet that comes out, and its pH is either above 8 or below 6, then that feels really scratchy and irritating on the skin. And so we had to make sure that our chemicals were properly balanced so that our pH out of these laundry machines, these giant laundry machines doing 36,000 pounds of laundry a day, were actually putting something out between 6 and 8. So we had to test our water supply, our clothing, to make sure that the pH was coming out right. Now we had spot testers, we could come through with a pH indicator and we could spray it onto a sample sheet, and that would tell us if that specific sheet had a pH outside that range. But, if we test that at the end of the day, well, we've done 36,000 pounds that day. We're not going to test all those sheets. We're going to test one, and if that's off, well, we might have 36,000 pounds that are off. We need a way to test inside the cycle where our pH is at. So we need to be able to take the water and actually test it. And that process is called titration. This is an extremely common thing that needs to be done in a lab setting, in industry. It's a titration is a method for determining. I'm going to run out of room here. Determining concentration of a solution. And that is particularly pH. Okay? So how does it work? Well, we've already looked at neutralization reactions. So the way a titration really works is we take some amount of substance. I'm just going to draw a Erlenmeyer flask here. There, my fantastically drawn Erlenmeyer flask. I'm famous for him. Okay, so in this flask, let's say I've got some acid. Let's say I've diluted it down so I know it's a low concentration, and then I need to know, what is that concentration? What is the pH of that acid going to be? Well, what I can do is, first off, I can take an indicator. So I can take an indicator, and there's lots of chemicals that do this. You can actually grind up cabbage, soak it in some boiling water, and that water will have a chemical in it that acts as a pH indicator. It'll change color depending on the pH of the substance. It's actually something that you can very easily do at home. If we'd still been in school, we would have done this in the lab. So we take an indicator and we put it in here. Now, a lot of indicators are meant to kind of spot check and not get an exact pH. So it'll change color. It might be a light green or a dark green or a purple or a yellow or something like that. I'll go to the lab today and I'll make a video showing some examples of what a pH indicator might look like in varying pHs. So once we've got an indicator in there, when we're doing a titration, we're going to be using an indicator that is very exact. An example of that might be phenolphthalein, which is hard to say and hard to spell, so I'm going to give it a shot here and I'm going to spell it wrong. But it's phenol, and it's phthalene. I'm not making this up. PHTH, that's actually in there. So phenolphthalein is extremely useful as a pH indicator because when its pH is below 7, it is completely clear. When its pH is above 7, it is bright pink. And so we're able to use a substance like that. And when we change the pH in here, as soon as it fully neutralizes, it will shift like that. The color will suddenly change completely throughout the whole solution. It's actually really cool to see. So once we've got that indicator in there, we'd use phenolphthalein, and I'm gonna go through an actual titration on video and send it to you guys so you can see what it looks like. Once we put that phenolphthalein in there, then what we do is we take a base, very common. Let's just use NaOH again. So we'd take NaOH, and we would make a known concentration of that. So once we would know the exact concentration of the NaOH that we are putting in there. So we would know our molarity. So we would know that. We would know that molarity. And then we would slowly start to drop it in, just drop by drop, until this gets fully neutralized. How do we know when it's fully neutralized? Well, the solution will suddenly change color. So we would go from clear to bright pink, just like that. And so the molarity of this base is known. So once we do that, all we're doing is measuring the volume of base that we had to put in to get that change. So then the volume of base is known. Once we know that, it's simply a matter of that neutralization reaction. So then I could say, if let's say this is just hydrochloric acid, so I'd know that NaOH plus HCl is going to neutralize to make H2O and NaCl. Okay, I know that this is the reaction that's going to happen. So when I add enough base to get this sudden transition, I know that I've neutralized all of this HCl. So I know my concentration of base, and I know the volume of base. So I take my concentration, that would be, let's just say it's 1 molar, and let's say it took 10 milliliters. Well, I can take these two values. Remember that to calculate concentration, it's going to be our molarity. It's going to be equal to our moles per liter. So I can use that. I can take my molarity times my volume, and that'll give me my moles. So then I know I've got, here I would be 0.01 moles of NaOH to fully neutralize HCl. And then I would know what volume of HCl I used here. So then I'd know this was also 0.01 moles because it's a full neutralization reaction. It's got to go that way. So then I know it's 0.01 moles. And then I would have measured this initial volume. So then I would know the volume here. Let's just say this is also 10 milliliters. And then I would know that the concentration, the initial concentration, must have been 1 molar. And then I can determine the pH from that. This 1 molar would be a pretty high pH. But regardless, this is the method that we would use to figure out the pH of that initial solution. So this is an extremely common way to test what the pH of a solution is, or the concentration of various other solutions. So let's look at an example here. A titration is going to give you a problem. Let's say we start with, let's say, 15 milliliters of HCl at an unknown concentration. And then we add 5 milliliters of NaOH at a concentration of, and let's say 0.0015 molar. So that'll end up giving us a pretty decent pH. So we just set up our neutralization reaction. So it's an NaOH plus HCl makes H2O plus NaCl. There we go. So that's our neutralization. We can see that everything is a 1-to-1 ratio. So if I figure out the number of moles of NaOH that was used, then I immediately know the number of moles that HCl of HCl that there was. And then I can take that, divide it by this volume, and I'll have the concentration, and then I can figure out the pH. Okay? So let's go through and do that, and then I'll show you kind of a shortcut. So first, how many moles of NaOH do we have? Well, we've got a concentration of 0.0015 molar, and we've got a volume of, and we're going to put this right into liters, 0.005 liters. So I've got, remember, to figure out the moles, it's going to be molarity times volume. So it's 0.0015 times 0.005. So that's going to be 7.5 e to the negative 6 moles. Okay? That's going to be, let's use black. 7.5 e negative 6 moles. And because this is 1-to-1, then the HCl, that's the number of moles of HCl that I had. So it would be 7.5 e to the negative 6 moles. That doesn't really look like an M, does it? There we go. So then I have 15 milliliters of HCl. So I'm going to take this and divide it by my volume. So I'm going to take 7.5 e to the negative 6 divided by, and I need that to be in liters, so 15 milliliters is 0.015 liters, 0.015. And so my concentration is going to be 0.00005 molar. So there's our concentration. We could also say 5 E negative 4. And now we could figure out the pH of our initial solution. See, we don't even need to do any work on this side of the equation because we only care about this ratio right here. We just need to know that this is where it ends up getting to. So that 5E negative 4, let's do our log. It's going to be a pH of 3.3. So our pH, there we go. So that's how a titration works. That's how we solve a titration problem. Now, a shortcut is to recognize that, well, my number of moles is going to be the same. So I've got, let's grab another board here. So if my number of moles is going to be the same, then let's just say, let's write out our general form for figuring out concentration. That's going to be C for concentration equals number of moles divided by volume, right? We did that before. We did some calculations with that. These are just the representative variables. So in order to, if my number of moles are the same, let's say N1 and N2. So my N1 is equal to N2. This is the number of moles of NaOH is equal to the number of moles HCl. These would be equal. Well, that means I can rearrange this and say that the concentration times the volume of my NaOH, let's just label this NaOH, is going to be equal to the concentration times the volume of the HCl. So I'm really just doing a pretty simple math equation here. So I'm going to take my concentration, which I figured out, I already knew that, times my volume, which I determined experimentally, and I'm going to divide that by the volume of my HCl, which I already knew, and then I would get my concentration. So this is kind of a shortcut math equation to do all of this work.